Hi everyone, this is going to be our notes video, part 8, and I'm going to be talking about acid and base titration. So when we get down to part 9, I'll start talking about the calculations that go with acid and base titrations, but for now it's just going to be very general. So in a titration, which all of you have done with me before, we use an indicator to locate our equivalence point, or at least approximate our equivalence point when we do a neutralization of an acid with a base. Now, an indicator is a weak organic acid that changes color over a very, very specific narrow range of pH values. And it's usually used to signal an endpoint of a titration, because it's going to change if you pick it correctly around that equivalence point. Though it will not change exactly at the equivalence point, because where an indicator changes color and the equivalence point in a titration are technically different things. Our equivalence point is when our H plus or H3O plus ions are equivalent to our OH minus ions in solution. Now, again, if you pick your indicator correctly, you can pick an indicator that will change right about the same place that that equivalence point exists. But again, you have to pick the correct one. Now, a strong acid and strong base titration curves are going to have a very specific look to them, and they're going to have very specific features to pay attention to. So what I've done here is I have drawn out a basic titration curve for the titration of a strong acid and a strong base. And there's two of them because the two different graphs depend on what you're starting with. The one on the left, it would be starting with a strong acid and titrating it with a strong base, whereas the one on the right would be starting with your base and titrating that with your strong acid. Now let's take a look at some of the features of these titration curves. So this point here right in the middle, this is what we call the equivalence point. And this point is generally found in the very, very steepest part of the curve. So you can see this curve is entirely vertical here. And so that point, known as the equivalence point, would be the midpoint of that curve, or that line, I should say. Now, because we're starting at an acid, over here on the left down at 1, our pH is starting low. In the interim space on the curve between here and the equivalence point, you are going to find mostly H plus or H3O plus ions. And the reason for that is because the net ionic equation that we are looking at here for this neutralization would be H plus OH minus in equilibrium with H2O. That would be our net ionic equation. So at this point, we have not yet added enough base, enough of this to neutralize all of these H plus ions. So at our starting point at 0, if you look at the label for this x-axis, at 0, that means we've added 0 base. So at this point, the only thing present in that solution, other than whatever spectator ions you might have, would be our H plus, H3O plus. And then as you start adding base, those OH minus, those hydroxides, are going to latch on to those loose protons, and they're going to form neutral water. But until you hit the equivalence point, there's going to be more H pluses than OH minuses. At the equivalence point, the thing that you have in that solution is mostly water. And the reason for that is because when H plus and OH minus are equal, that's just water. You might have a little bit of autoionization going on because it is in equilibrium, and that does happen, but most of what you'll see at that equivalence point is water. Now up here in this section up there, that is where you have then exceeded the equivalence point, and now you have mostly OH minus ions there. And you can see that reflected in the dramatic increase in pH that then levels off around 13 here. Over here on this graph, we have the exact opposite happening because we have started with a strong base, which we are titrating with a strong acid. Now our pH is starting strong up at 13 over here on the left. And at that point, again, we've added exactly 0 acid to this strong base, so its pH is high. In the middle here, that is where our H plus and OH minus are equivalent to one another. So again, we have mostly water here present at the equivalence point. That's mostly water. Then down here, we have exceeded the equivalence point, and we are mostly going to be H plus ions. So once again, to label that, this distance, that's going to be mostly H plus. This distance up here is mostly going to be OH minus ions. Equivalence point is where those two equal one another. So strong acid and strong base titration curves are pretty easy to read. One important feature of strong acid, strong base titration curves is that their pH at equivalence is 7. And the reason for that is because when you have a strong acid and a strong base that are ionizing completely, the only thing at the equivalence point is water, and water has a pH of 7 because it is neutral. So this lone product, that is the reason for that pH of 7 when H plus and OH minus are equal. So pause the video and go ahead and copy that information that I have here into your own notes if you have not already done so. To move on to our other titration curves, the first one we have to talk about is weak acid and strong base. So here is our graph. You're going to want to pause the video as I go and copy down the information onto your graph. All right, so once again, I have a basic titration curve. This time, though, it is for the titration of a weak acid being titrated with a strong base. So let's analyze that real quick. Over here on the left, we have a weak acid, and so our pH is starting off a little bit higher at 3. Our equivalence point found right here in the middle, where our concentration of H plus and OH minus should be equivalent to one another. And then over here, once we have far exceeded our equivalence point, we have our final pH of about 13. So our equivalence point is still where H plus and OH minus equal one another. So we can go ahead and label that the equivalence point. But there is something different about this equivalence point. So you will notice that our equivalence point is no longer at a pH of 7. Now, if we trace this over, our equivalence point is actually hit at a pH of 8. And the reason for that is revealed from this equation over here. So when we are titrating our weak acid with our strong base, again, this is a net ionic equation. When our H plus and OH minus are equal, we have water, but also A minus. We have our conjugate base present at equivalence, whereas we were not seeing that with the strong acid and strong base. So this conjugate base present at the equivalence point actually pushes the pH a little bit higher than 7. So at your equivalence point, your most common things to find in that solution are going to be water and A minus. Those are the only two things that you're going to find in high concentrations there. So if we trace that down, we'll find the volume that it took to reach that equivalence point. And that sometimes you will see abbreviated VEQ, volume at equivalence, volume of base added at equivalence. And then if we actually move over to the left and we take 7 and cut that number in half right here, this is known as our half equivalence point. And I'm pointing that out because if you trace this half equivalence point up to our titration curve, it is at this point that our concentration of weak acid and our concentration of conjugate base are equivalent to one another. So on your graph, I'd like you to label that our concentration of HA, and again, that's our weak acid, is equal to our concentration of our conjugate base. Now that's important because we have to think about the Henderson-Hasselbalch equation. And so to remind you what that is pH is equivalent to the pKa plus the log of conjugate base concentration over our acid. All right. So if we look at this equation and we consider what this term here means on the right, base over acid concentration. At this point that we're talking about, at the half equivalence point, if these two concentrations are equivalent, that means that we're going to be taking the log of the number 1. And the log of 1 is 0. So that essentially negates this entire term right there. And at that particular point, pH is equal to pKa. That is a popular question that I've seen a number of times in past APs. That point and relationship to the Henderson-Hasselbalch equation. So not only is this point the point where HA and A minus are equivalent, but it is also the point where pH equals pKa. So go ahead and label that on your graph as well. Next, we're going to go ahead and label what species are most prevalent at what points on this titration curve. So from the start of our titration here at pH of 3 up until our half equivalence point, so that's this area right here, our concentration of our weak acid is going to be greater than our concentration of conjugate base. And that makes sense really, because at this point, we have not added a ton of base. So we mostly have weak acid. And then we hit the half equivalence point in which our concentration of weak acid and our concentration of conjugate base are equivalent to one another. But then after that, until we hit the equivalence point there, that's when our concentration of conjugate base is greater than our concentration of weak acid. So go ahead and label that on your notes as well. Then we hit the equivalence point where all we have is water in our conjugate base. And then after the equivalence point, if we keep dumping base in there, you're mostly going to have strong base in that. So you're mostly going to have OH minus ions at that point after our equivalence point. All right, so last bit of information that I'd like you to add is just a notation that at the equivalence point, our pH is going to be greater than 7 for this one. And I know that we have already kind of pointed that out over here on this graph, but I want you to make a special note about it as well. Moving on to our last graph that we have to talk about. This is going to be our graph where we take a weak base and we titrate it with a strong acid. So once again, go ahead and pause the video right here and we're going to label it. All right, so once again, go ahead and pause the video and copy all of this down so that you can label along with me. Looking at this titration curve, we're starting out high, which means we're starting out with a base. In this case, since we're starting out at pH 11, we can tell that this is likely a weaker base. And then we start adding some acid to that and we hit our equivalence point right there in the middle. And then our far exceeded equivalence point right over there at the end point at 13. Now, our equivalence point remains the same as it always has been. Our equivalence point is 1H plus and OH minus ions are going to be equivalent to one another. The equivalence point here, you will notice, is at a lower pH than 7. So label your equivalence point and that the pH is smaller than 7 for this one. That's going to be important. And if we look over at our net ionic equation over here like before, it can kind of become apparent as to why that is. because here, when those two things are equal to one another, we have acid present in solution. And so when we have acid present in solution, that pH is going to go down a little bit. So it's not perfect neutrality at that point. Instead, it is slightly lower than neutral. All right, and let's go ahead and trace that equivalence point down, and we're going to label VEQ just like we did before. We're going to go over to half of VEQ, and we're going to trace that all the way up to our half equivalence point and label it there. Now, once again, our half equivalence point, that is where our HA concentration is equal to our A minus concentration, and it is also where pH is equivalent to pKa. Okay, now this titration curve is essentially a flipped version of the one that we just did before. So whereas on the one before, this area from start to our half equivalence point had a higher concentration of HA than A minus, in this one, it is flipped. So here we would have a bigger concentration of A minus and a smaller concentration of HA, which again, if you look at this net ionic equation, makes sense. We've barely added any acid at all at this point. So the thing that's most prevalent in solution is this guy right here, or A minus. Now, after the half equivalence point, when HA and A minus equal one another, we have a region of space where our HA concentration is going to exceed that of A minus. And then we hit our equivalence point where you're mostly going to have water and HA present, which again, that is why that pH at equivalency is slightly lower than 7. Now, after that, after we keep adding acid, down here in this region of space, the thing that you are going to find most prevalently is going to be your H plus ion, because your H plus ion is that part of the strong acid. Now, depending on what your strong acid is, you might also find some anions down here, just like in our graph above. When OH minus was most prevalent, you're also probably going to find some spectator cations there. So on an AP test, if it asks you what is particularly prevalent at what point, you have to think about, okay, well, what was originally attached to this H plus ion? So if you're in this region of space and you know that the strong acid you've been adding is HCl, well, then you're going to have H plus ions over here, and you're also going to have Cl minus ions there as a spectator. Just like in the graph above, when our titration curve looked like that, up here was OH minus ions. Well, depending on what your strong base was, let's say it's NaOH, your other ion that's super prevalent at that point should be Na plus, again, as a spectator. So those are the kind of things that you have to think about when they are asking you questions on an AP exam. So once again, if you have not yet labeled all of these things, go ahead and pause the video and label it all on your note set. And that is where we're going to stop for right now. Next, we will talk about calculations associated with titration curves. If you have any questions, please ask me in class.